嗯，零，它不好吧？嗯，看得到吗？你没有看过这新闻吗？懂完的，我学生也没有看。哎，我哦，嗯，有单东西，你都在厉害，那你打呗，直接回去打，就上要做，什么叫要做梦？没有做梦。 也只能上到很水管。上对对吧？哎，宣传。那个，今天真早起来，你们。早餐。你不用习惯，都正常。对啊，对对对对。反正因为我们是底雷，那个大雷是什么？在关键啊，我在看关键是。少很多东西。Okay, good morning to everybody here. Actually, our lecture is a bit delayed for the midpoints compactness and sequential compactness because we spent a lecture discussing our midterm. So I wonder, do you guys need extension or you guys can use MA2 knowledge to solve it? It's actually MA2 stuff. The last question. What do you think? How's your progress on your assignment? You guys need extension or not? Don't need, huh? Okay, some of you know. So if you need extension, you just let me know. Okay. Mm, I think it's reasonable if I give extension until maybe next next Tuesday, next Thursday. By then I should finish everything about sequential complex stuff. But really, the last question is MA2 stuff. And we will generalize the result in MA2 to metric space instead of just Rn. So if you don't need, if you need extension, you just email me or message me. Okay, if not, you just follow the usual deadline. Okay, and I hopefully by this weekend, and I will give out next assignment so that you can start earlier. Okay, maybe we start first and then we can discuss other stuff. Yeah. Right. Okay, let's start first. Right. Yesterday, we finished up with this theorem here. I asked you to go back to read yourself, which is if X is a non-empty, okay, compact cross dot space, okay, and moreover, this space here has no isolated point, then X is uncountable. After I go back and review this proof, right, seems like it might be helpful for your assignment 6. Last question. Similar argument. I wouldn't say the same. Please don't think about straight away adopt this proof, okay? It's similar idea. Okay, similar idea. So let me quickly prove this to you. All right, so this proof can be split into 2 steps. Okay. So we will show that given non-empty open set U of X, okay, and any point, okay, of X that exists a non-empty set, and non-empty, moreover, this set is open such that this V is in U and S is not in the closure of the set. Okay. We will first do this. Okay. Can everyone get what it says? Okay, so if you have a set X and then you find an open set U, space X, and then you have open set U, and then you take any point in this space X. Where can this point be? Even this picture here. Where can the little s live? Sorry? Everywhere in X. So how many possibility here? 2 possibility, right? Either inside you or outside you. Okay, either inside you or outside you. Good. Okay, either inside you or outside you. And then the claim is there exists an open set V such that this V lives inside U. Okay, and then the closure of V doesn't intersect with the singleton set X. Okay, so you can find some V maybe like that. Okay. Such that the closure of it avoids X. Does it make sense? Okay. I will prove to you how to do it. but you need to understand what I want to do first. Okay, make sense? Okay. Once you do this, okay, the step 2 is, so the step 2 is, we will show that given any map, okay, given, we want to show that it is uncountable, right? So in particular, we want to show that it is infinite and not countable. So let's say if you have a countable map, being mapped from a countable set to X, then the function is actually not surjective. Okay. You can find more things than this denumerable things. Does it make sense? Then it will follow that X is uncountable. Can everyone follow the logic now? Okay, I haven't tell you how to put these two together, but once I do step 2, we should get X is uncountable. Does everyone agree? Yeah. Okay, good. So let's check step 1 first. Let's do step 1. So what is step 1 here? Okay, we want to show that for any non-empty set U of X and any point X in X, there's this V not empty such that V is in U and X is in the V closure. So how should we start here? So I mean, our set is non-empty. Okay, our set is non-empty. And our set is a topological space, right? So you should be able to find an open set there. Okay, does it make sense? So pick. So I mean, just fix any open set U of X. Okay. And we want to show for any point in X, right? So also fix any X in X. Okay. Just take a space, pick an open set, pick a point in your space. Then we can choose Y in U such that Y is not equal to X. Does it make sense or not? Can we do that? Is it possible that this U only contain X or not? No, right? Because there's no isolated point here. So you must find some Y such that Y is not equal to X. Okay? And this X, like what we discussed just now, maybe inside U, maybe outside U. Okay? Maybe inside U, maybe outside U. Okay? So this V cannot contain, wait, let me see. What's this? Did I write something weird? Okay, you see here, what I say and what I wrote is different. X is not in this V bar. So how should you think about this V open set here? It is not containing X. It should be avoiding the X, maybe something like that. Okay, should avoid it. Okay, let's see. So so you can choose Y in the open set such that Y is not equal to X. Okay. And then what can you do here? Can you start finding open set that separate X and Y or not? Because our space is Hostov, okay? So now, what do we do? Now, we choose disjoint open set W1 in X and W2 in Y, okay? Such that W1 intersect W2 is empty. Because our space is compact Hostov. Hostov says for any 2 points you can find 2 open set that contain each point separately and then their intersection is empty. Then what is our V here? Can you recognize what is our V here? how can we set our V here in this case? So let's say we have a Y on this side, okay? And then we have W2 here, and then we have maybe W1 here. So how do we set V in this case? What's the V that contain in U and the closure doesn't contain X? How do you set the V now? Hmm? Can you take W2 or not? W2 might not be contained in U, right? So what can you do? Okay, do. Yes, intersect them. Okay, so you can take V equals to W2 intersect with U. Okay, so this is a set in U in particular. And of course, you need to argue why X is not in the closure. Is it clear that why X is not in the closure or not? What is the closure of V? It is the interior with the boundary. Okay. So we already proved that it is not in the interior, right? Because the intersection is empty. But could it happen to be at the boundary or not? Is it possible? Possible or not? Is it possible? Is it possible that it happens at the boundary and then you still can find an open set that separates the two? Cannot, right? Because if you are at the boundary of that ball, meaning what? Every neighborhood you should contain point in A and complement of A. So you cannot find open set, historical set that separated. Okay, so it cannot be at the boundary as well. Okay, so it cannot be at the closure. Okay. Okay, good. So we can do this. So given a point X, given a set U, I can find a point Y such that I have an open set that separate these two numbers and then such that this special property here for. Okay. Okay, good. So what do we do next? Okay, so second step. Let's say we given this function here. Okay. F from Z plus to X. So what can we do here? So from this map here, what can we have is we have a sequence of points. Here we have a sequence of points here. Maybe you consider F1, F2, F3, F4, F plus. So what is plus here? Actually, these are the, let's say we just put it as a natural number. It's just a positive integer, which are the natural number. So F1, F2, F3, F4 give you a sequence of points. So what can you do here? Okay, so we can apply step one. Okay, so how do we do step one here? So we can use step one to the non-empty open set U equals to X. Okay, we can use this step one here to the whole set. Okay, what do I do here? To choose, okay, to choose V1 in X such that V1 bar is not in, sorry, it doesn't contain X1. Okay, so this is what I can do. Correct or not? Does it make sense? I'm using step one here. Recall what we did from first set one. I have an open set. I have a point in X, and then I can find an open set that avoid this point. Make sense? Okay or not? Question? Got question or not? Okay. If not, what can we do next? So V1 in particular is a new open set, right? Okay, it's a new open set. Then what we can do is again we apply the step one to this open set. Okay, and what? And S2. Okay, so we will find another open set that avoid x2 and x1. Okay, so in general, so given Vn minus 1 open and non-empty, we can apply step 1 inductively to choose Vn to be a non-empty open, non-empty open set such that Vn contains in Vn minus 1 and Vn bar doesn't contain Xn. Does it make sense? Okay, so in this case here, what do we have? So and in this case, what we have is a nested sequence. So how does this nested sequence looks like? We have a V1 bar containing V2 bar, containing V3 bar, and then we keep doing it, and so on. Okay, so these particularly are the nested sequence of non-empty closed set of X. Right, we have this nested sequence of a non-empty closed set of X. What's the closed set definition for compactness here? Anyone can recall? What's the closed set definition of compactness? Last time we deduced the equivalent definition for compactness using closed set, right? About intersection, something about intersection of closed set. Let's recall that. Compactness and then compactness. Okay, somewhere around here. Here. Okay, if F is a collection of a closed set such that every finite subcollection has non-empty intersection, then the whole intersection of your closed set is non-empty. So just now we have a nested sequence of closed set. So if it's nested, right, then it should hold through the every finite subcollection should have non-empty intersection, because if you just intersect finitely many of them, you just get the smallest one. Okay. So in this case here, by closed set definition of compactness, I can find something inside the intersection of Vn. N equals to 1 to infinity. Okay. Are we done or not? Up to this stage? Are we done or not in this stage? How special is this limit point here? Can this point come from any of the Sn or not? How do we build Vn? We build Vn to avoid all the Sn, correct? So, but x is not equal to xn for all n, right? Since s is in Vn bar. Moreover, xn is not in Vn bar by construction. So you found a new point, okay, that's not met by your function from countable set. Does it make sense? QE. Yeah. This new x here is not coming from the image of your f. So the corollary, like what I said yesterday, the corollary here is every closed interval in R is uncountable. Okay, because every closed interval in R is compact. We showed last time. It's Hausdorff, should be not hard to show, right? You can find the distance between any two distinct points, and then you can build two open interval that avoid each other. Okay? And what? It has no isolated point. Correct? Because you can use density of rational and irrational numbers, okay, to find points between two real numbers, which is also real. Okay, so it satisfies all the property we had for this proposition here. Does it make sense? Okay. So you see, last time when we show that R is uncountable, how do we show it? We use Cantor diagonalization theorem. Okay. So the Cantor diagonalization theorem, you can think of it as this part, the second part here. We are trying to build a map from natural number to the real number. Correct? We want to list them. Okay. And then somehow we can list new numbers. Okay, in that Cantor diagonalization theorem. But in this case here, how do we find the new number here? We look at the intersection. Okay, we look at the intersection to find the new number here. But one differences that we show R is uncountable is we only manage to show that only closed interval is uncountable from this corollary. So the closed part here is kind of quite important in this case, because what we really use in the previous proof is we use that the space is compact. Where we use that the space is compact, but R itself is not compact. One point can be recognized as a closed interval. You mean it is not uncountable, but is it counted as an isolated point or not? Counted as Hausdorff space or not? The compact. Hausdorff. Not isolated. Because one point set is open, right? Yeah. Isolated definition is of one point. A point is isolated if one point set is open. Yeah. Yeah, I think good point, very good point. You can try and attack this. If you try and attack this theorem, right, maybe you'll come out with a lot of nice examples. How these properties stick together and they will give you like infinitely many. Okay. Yeah, it's good to think in that way. Right. Good. So finally, before that, we will run through local compactness first. Okay. let's quickly run through local compactness. And there's one very important result that I think I don't want to prove it first. I want to leave it for next time, for a longer time. And I want to jump to sequentially compact stuff first so that you have brief idea. I mean, maybe help you to recall what you had from MA. Okay, so let's quickly run through this local compactness. The slogan for this part here is, so you can think of it, last time we introduced connectedness, right? We also introduced local connectedness. And local, what was the use of local connectedness? Do you still remember? When is a local connected half component is a connected component? When is half connected component a connected component? Because we have an example that a space is connected but not half connected, right? When these two are equal, it is exactly when the space is locally connected. Then these two things will coincide. Okay. So similarly here, so why do we introduce this local compactness here? So the slogan here is any locally compact Hausdorff space. Okay, so in topology, right, usually we like to work with Hausdorff space. Otherwise, there's a lot of maybe exceptional coming out. So any locally compact Hausdorff space can be embedded. So you can think of this embedding as a like injective map. Okay, embedded in a certain compact Hausdorff space. Okay. So meaning you are maybe locally connected, but I can put you inside a compact space. Okay, but it works for Hausdorff for now. And this space, right, is a special space that we call the 1-point compactification, okay, of the space. So this 1-point compactification is compactification of X. So what's this X here? X is this locally compact Hausdorff space. Later, I'll give you some very nice example. Actually, we have seen example already, but now I want to make it more precise. All right. So can everyone remember this slogan here? Remember this slogan? We want to work towards this slogan. Okay. You don't understand, that's fine, but you need to know what we are trying to do. Because I'm going to tell you what is it. Can follow? Everyone remember this slogan? I can put a locally compact Hausdorff space into a Hausdorff space. I mean, compact Hausdorff space. Locally compact become compact. Okay, so let's define what is it a locally compact space. Do you want to guess? By referring to local connectedness. Want to guess this definition? How is it locally compact at one point? If there exists a compact subspace C of X that contains an open neighborhood of X. Okay. So a space is locally compact at X if you have compact subspace of X that contain an open neighborhood of X. Okay, so you can think of it as a point X, okay, and then maybe you have an open neighborhood of U, okay, and then this open neighborhood of U is contained in a compact X. Okay. And if X is locally compact at each of its point, Okay, every point it is locally compact. Then we will simply say that X is locally compact. We didn't mention the point anymore because it is everywhere locally compact. For example, what spaces are locally compact? Real number is locally compact, right? Okay, let's put here. So why real number is locally compact? Why real number is locally compact? Sorry? Every subset of it is sum of it. Open interval is compact. Open interval compact or not? Sorry? Closed interval is compact, right? Right. So if you want to show that R is compact, what do you need to show? And every point it is locally compact. Okay, so for every point to be locally compact, you need to produce this picture here. Correct or not? Okay. So for every point in R, what do? You would have a open interval that contains it, and then you can embed this open interval into a closed interval, which is okay. But more generally, actually, a compact space is automatically locally compact because the space itself is the compact subspace. Okay. The space itself automatically locally compact. Okay, so but there's one space it is not locally compact. Okay, actually, Q is not locally compact. Q is not locally compact. Why Q is not locally compact? What do you need to show if Q is not locally compact? So to show that Q is not locally compact, then you need to show the negation of the statement here. Okay, negation of the statement here. So there is a point such that no compact subspace will contain any neighborhood. Okay. So should we discuss about this? Let's just show for 0. Okay, let's just look at 0 point first. So suppose other points should be similar. Again, let's look at the point 0. Suppose for the sake of contradiction that Q is locally compact at x equals 0. Then there exists a compact C and open U such that a 0 is inside this, let's say, minus epsilon to epsilon, okay, the intercept Q. And this thing is in U, right? Because U is open, you can find some epsilon ball inside there. And this U contains in C. And then this whole thing happens in Q. And for some epsilon. So I want to produce a contradiction here. What should I contradict? I should contradict that this C actually is not compact. Okay. So to show that C is not compact, right? What should I do? I want to produce a open cover for this C such that it doesn't have a finite subcover. Okay, so what's the trick here? So the trick here is like how you show Q is not, how to show Q is not compact. You can use your previous knowledge. You can use the sequence definition, right? Every sequence has a convergent subsequence. Okay, but what kind of convergent sequence you have in Q? Either you converge to rational, either you converge to irrational. But if you converge to irrational, then the limit is not in the rational. Okay. So we want to use this kind of argument to produce an infinite cover here. Okay, we want to use this kind of idea to produce an infinite cover here. So here's my claim. Okay, here's my claim. So let's choose an irrational, okay, W inside this minus epsilon to epsilon. Okay. Then what do I do here? Okay, so let's draw some number line here. Let's draw some number line. We have 0, right? We have minus epsilon and then to epsilon, right? And somehow we found one irrational number around here. So what can I do here? So this is my claim. Then I can find an n such that this n should be the minimum of 1 over absolute value of epsilon minus w, comma 1 over w plus epsilon. What am I doing here? I want to compute the distance between w and epsilon. Okay, so that I can write my C like this. So I can write my C as C taking away w minus 1 over n plus epsilon, comma w 1 over n plus epsilon. Okay. So what am I doing here? So let's draw this up. Where is my w minus 1 over n plus epsilon? It should be around here. Okay, so let me draw it here. W minus 1 n plus epsilon. W. Okay. Where's my C? My C is maybe somewhere outside. Okay, C. C contains all these things. Okay. And then what trick I play here? Let's check whether my trick works or not. So the trick I want to play here is this. So I will set the so what have I done here? So I already covered this part and this part. So how do I cover the middle part here? Everyone see? How do I cover this middle part here? Okay, so this is a trick I'm going to play now. Increase the n. Okay, so let me write down and then I tell you what am I doing. See whether it makes sense or not. So I'm going to take union, okay, of a set looks like this. W minus 1 over n of w minus half times 1 over n plus 1 plus 1 over n plus 2. Okay, union with w plus half 1 over n plus 1 plus. Please follow first. Later I'll tell you what am I doing until w. Or at, okay, look at it first, and then I'll tell you what am I doing here. Okay. I haven't simplified this part. I purposely don't want to simplify it yet. Okay, so what am I doing here? So you see, what am I covering for the first union here? I'm covering everything outside W minus 1 plus 1 over n plus 1, and then W plus 1 over n plus 1. So what I do is I want to create infinite cover in the middle. Okay, how do I do this? This trick is the one that we used last time. Okay, so let me draw it here. We have W minus 1 over n plus 1 here, and then W plus 1 over n plus 1 here, and then maybe W is around here. Okay, make sense or not? Make sense? Okay, so now I want to create infinite cover here that cannot be reduced to a finite cover. Okay, so what do I do here? So sequence, right? So what can I do is, if you look at, we have first few points here, f w minus 1 over n plus 2, and then w minus 1 over n plus 3, and then so on, right? Okay, similar from the right-hand side, I also can do the same. W plus 1 over n plus 2, w plus 1 over n plus 3, like that, infinitely. All right? Because it should converge to w, right? 1 over n. Okay. Okay, let me finish first. Okay, and then what do I do is I can start the first covering here, cover all the way from w minus 1 over n plus 1 up to the middle point of w minus 1 over n plus 2 and w minus 1 over n plus 3. Does it make sense? I cover up to the middle part here. And then I start from w. Let me use different color. So I cover here up to the middle point here. And then the next cover will start from W minus 1 over n plus 1 up to middle again. Right or not? This is how we show R is not compact, right? Okay, so we keep doing this. Okay. I keep doing this. And then similarly, I do from the right-hand side, is the same, like that. Okay, I keep covering it. But not that, not that. Inside here, there's no one containing W, but that's fine because our set is rational. No need to cover W as well. Okay. But my claim is this is equal, and then you cannot reduce the infinite cover here. If you take out any infinite cover, I mean any open set from this infinite cover, you should miss out some point inside the C. Does it make sense or not? Question? 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 You can also ask about this notation here, whether it makes sense or not. But do you know what am I trying to do from this picture here? Okay, I'm just trying to write this picture into this formulation. Do you understand what I did in this picture here? Understand? Okay. Yeah. Okay. Got question? Question? Any question? So you can think of this W is the point that we avoid. But anyhow, this compact set won't contain this W because it is irrational. Okay. But thanks to this point here, we can create this infinite cover. Otherwise, you can think about how we show the closed interval is compact. We also have this kind of cover, right? We can cover bit by bit, bit by bit, bit by bit, bit by bit. But the problem is that in the compact set is what? The supremum exists. The supremum of the set that you can cover the interval by finite set exists, which is the endpoint. Okay. But here, once I take away this W, there's no endpoint already. You have to keep going. And you will never reach W also. This is how we show R is not, because we can keep creating the open set. If you remember, is K to K plus 2, right? K to K plus 2. Because K plus 2 will never reach endpoint. It will go infinitely many. But now you go infinitely small. In real number, you go infinitely large. But in this case here, you go infinitely small. You want to approach W, but you never approach it. Okay. Yeah, any question? Yeah, I invite you to check this Ignite cover. I think it works. If it don't works, only problem will occur is this equality here, unless this equality is wrong. So not that I want to intersect with rational here because we only care about rational. Okay. Any question? Not yet. If no question, we won't finish first. I will tell you the result about local connectedness. So, so it's quite restrictive to be locally compact Hausdorff. So the theorem is S is locally compact Hausdorff if and only if, okay, there exists a space X, so Y, sorry, call it Y, such that what? Such that X is a subspace of Y. Okay? And Y take away X is a singleton. And then Y is a compact Hausdorff space. Can you think of any example that we met looks like this? Recall the quotient topology example. Yeah, we have a closed D, right? That we can map that we can create a map that you send the boundary to one point. Okay, so in this case here, what we can say is the open ball. Okay, the open unit ball is what? Is sitting inside the sphere. Okay, it's sitting inside the sphere. How does it sit? So we'll say that, okay, so this is the definition of one-point compactification. So definition, if Y is a compact Hausdorff space, and X is a proper subspace of Y, so closure is equal to Y, such that X bar is equal to Y, then we will say that Y is a compactification. Okay, so maybe you are not a compact space, but if I add in the closure, you become compact. Okay. Say if you become compact, then we will say that Y is a compactification of X. But in this special case here, if you only need to add one point, okay, if you only need to add one point to make it compact, then we will call it a one-point compactification. Okay, so this is special about this locally compact space. You only need to add one point. Okay, it will sit inside a compact space. Okay. So then we will call this Y as the one-point compactification. And in general, maybe you need to add few more points, but if it is just 1 point, then we call it a 1 point compactification. So I mean, let's take for some example here. This idea is quite, how to say, quite important in the mathematical research. Okay, we were interested in looking at compact space. Okay, if the space we are working in is not compact, we want to ask whether there's a compact space it works. And so let's say real line. Okay, real line is not compact. Okay, imagine if I add a point into this real line, what could it be? Huh? You will get a circle like that as well. Okay. Typically, we call this point infinity point. Okay, if you add infinity point into this point, is compact. Correct or not? Because the problem in real number is the sequence that diverge, right? If I say, oh, infinity point is not divergent anymore, you still converge. Then I got this circle become a loop. Okay, it becomes a loop. And then, so that's why sometimes like you'll see people say negative infinity, never mind, is the same. It's this reason here. Okay, we make 1 point that represents the both end. Okay, it's this reason. Okay, and let's say last time we talked about the open ball, right? So this is a similar case. What if you have an open R2? Okay, you also add infinity point there. What do you get? Okay, what you get is the sphere. Okay, because open R2 should be homeomorphic to the open ball we have last time. Yeah. Okay. And then similarly, if you take complex analysis, right? Let's say this R2 have a special property, meaning you treat the x-axis and y-axis differently. You have an I there. Y-axis, when you do arithmetic, you have I squared equals to -1. So the property we look at in the complex analysis is about the conformal mapping. Okay, conformal mapping. You want to map the space by preserving the angle. Okay, preserving the angle between the vector space, which we call the conformal mapping. Okay, this is a very large topic in complex analysis. So in this case here, I add 1 point here. Still the same. Okay, we will get a sphere. Okay, but in this case here, we call it a Riemannian sphere. Okay, Riemannian sphere. Because there's some complex structure on this sphere now. Okay, Riemannian sphere. Okay, yeah. So this idea is very interesting and still ongoing, using in the research frontier about this 1 point compactification. I think in the textbook they also have this Stone-Z compactification. Hopefully, maybe we can talk about it later. All right, so far, any question or not? I think maybe we won't prove this theorem because it's quite tedious and I just included in the notes. Okay, but the point I want you to appreciate here is how to, what's one way to get 1 point compactification. Okay, it's through this locally compactness. Yeah, no? Yeah. Other than that, you don't need to know much about locally compactness. Okay. The only thing you need to know about locally compactness is how it gives rise to a 1 point compactification. Okay, any question? Any question before we took a break? So after break, we will jump into the compactness in metric spaces. So generalizing what happened in Rn. As long as we have distance, then we can do limit point, we can do sequence. Okay. Okay, if there's no problem, let's take a break until 12:08. Thank you very much. For those who just came late just now, if you want to have a delay in your assignment, you can email or message me because we have delay in the lecture to talk about the limit point and the sequential compactness, which you need for your last question in your assignment. But if you can do it, actually that is just knowledge from MA2 is the same, just replace R and to X prime matrix. Yeah. So if you can make the deadline, you just meet the deadline. If you can't, I can give how to say kelonggaran. So I can give what's the English word? I can give lenient. Yeah, I can give you some lenient exception. Okay, to next, maybe before next Thursday. By next Wednesday, I should finish up all these compactness stuff. Wednesday. So you can do up to Thursday. No, you can continue discussing. Yeah, I just want to talk to those companies. Yeah, because not everyone need extension, so you just message me. Yeah, personally.
第一题啊，那是我就是这样子。separation，是我要在最发展这个门的是对在。
那你要 contradict 什么？不是你没有，你要
contradict 什么？我觉得
contradict disjointed。
它其实 contradict disjoint，但是我是 contradict 是什么？
那你就要 argue 啦，什么 contradict separation 啦，对不对？
因为他们 contradict 有 disjoint 啊，我觉得
没有，不是写两个。现在你的问题感觉给我是说，你不知道为什么那个
separation，
对呀，
因为 separation disjoint，
那就好了。
所以我讲 contradict 它是 separation。
你就讲 sin separation unique disjoint 那才是什么之类的这样吗？如果你要补回去的，什么来的？我也不知道。
第一题啊，那个 x 或 y 是原生 ，x 和 y 原生，它的两个 x 大学对。
什么？
感觉我的 argument 有问题。
有问题？哪里有问题？
就是我 assume 它是 not subjective 啦 ，and then 你就有这个东西咯。跟就是你就拿一个 point outside 这个的。
对，那个昨天讲
啊，然后 and then 我用这个，然后我直接去这边，我觉得问题就是，因为你摆那个 isometry 嘛，你这个你可以 你就可以
每个都一样
这样子，
都一样。
然后我直接 claim 这个 there means no sequence in x converge to x， 然后我又讲它是不 subjective， 是不是有问题？
应该讲它是没有，它应该讲它是没有那个 subsequence converge to any point in 的，它就还没有 converge subsequence 的，你应该 contradict 这个啊 contradict to compact。
对，那个 sequential 那个 sequence 没有 subsequence
啊，对，没有 converge subsequence， 对，
没有 converge subsequence，
这种东西你可以 prove 到它。
可是by你这样子讲的话，你不是那个你这样子 check 的话，不是只有一个 subsequence， 因为你不是会有一些地方没有 check 到吗？
每个都 check 到，每个点跟每个点的每个点跟 任意两个点sequence 里面的任意两个点的距离都大于等于 t 啊，大于等于那个你写那个字啊。
那等
说出来。很大。
不，我是觉得，因为一开始 supposed to control 你讲 f 不是 surjective 的嘛，and then 你 fx is subset of x，and then 你就是有一些 point 你是没有 check 到的咯，就是 supposed to control 来讲啊，
有一个点啊，有
一些点在外面，这样子你把你这个 f 的 construction 来讲，你只是 check 到其中一个 sequence 它是没有罢了，然后你有一些 point 不一定是你 check 得到的，
我们可以 check 到全部啊，
可以 check 到全部吗？
可以 check 到全部。
等下好像你们的全部不一样。
这一题讲全部
就是全部
，x 里面的全部啊，
它的全部。
我的全部是 x 里面的全部，因为你要
是不是不一样？对呀，要讲清楚什么东西。
因为你要讲 x 没有它没有
首先是
subsequence
fx 这个东西它是 compact 的，对吧？
哦，要说这样 OK， 这样我知道，要 claim fx compact，OK，
这不知道
，OK，
对，只要他们两个懂就好。
fx compact 啊，
我 OK。
x 是 compact 嘛？
啊，
一开始有你的名单
啊，对，
我看到你 team 上面写
那个，不然的话回去
还是我的 construction 是
是人，我突然哦，它
对
不一定比较短，因为
就 S
比
较短，会比较短，只是说可能你要修它分的时候会比较难一点。不是不会难啦，不会难，因为你要 consider 的是
哦。
OK，
不 continuous，
没有过，但是没，
所以我可以把那个 x compact，
哎，不容易看，其实容易看。
然后
没有，你这个 set 啊，其实是 y 大于 x 上面，对，I mean y 大于 x 不是 fx 了。
and then
我想下
fx，我正在 check 的时候，我是 check fx 里面全部的点，fx 里面全部的点都没有 subsequent convergence，
叫做
and then 我就
x 大于，
你
看这边没有关系，所以其实就是 y 大于 x。你想讲的就是那条线的上面跟下面嘛。对，现在要讲的是这里，
那是为了去
OK， 你知道会 separate 对不对？现在你只要知道他们会
对
OK， 我知道，谢谢。
上面那个区域跟下面那个区域是 open， 对不对？你就要争这个 map， 对不对？所以 open 就是说每一个点你可以找一个波盖住它，那个波不会跑出来啊，对不对？在它的 interior。所以你怎么确保这件事情呢？其实你就是找了一个点，然后跟你的这条 y 等于1的线，应该就是那个 orthogonal projection 的这个。不，你要仔细很仔细的来做这个事情啊，就是你要找这个 orthogonal projection 的这条 length， 然后你就放一个波小过它，然后你要 argue 的是为什么这个波不会使得这条线出现，那就 OK 了。
两个人要死都要做自己。
那个 orthogonal projection 不好做哎。
好做，只是你要 argue， 你是
想不到他那个你是这样写，
因为你是正方形。
orthogonal projection 就是你 project 去那个意义的那个 basis vector 吧吗？意义，
我知道。
你最后要 argue 的是为什么你做的波会 avoid 全部那条线，肯定你是 avoid 那个点了嘛，但是问题是你怎么可以 avoid 其他线？其实这个就是 orthogonal projection 的理论。
定义咯，因为它最短的 distance 嘛。
所以你是要用到 linear algebra 的东西来。所以要用多细哈你 train open 就好了。OK， 好。Yeah, so wow. 没有，最近我还是有兴趣。Okay, so for the question, which question? Question 3. Okay. Question 3 in the assignment, right? So if you use the connectedness argument, right? So you try to use two open set to separate your image of F. So the two open set you use should be the set xy such that y greater than x or y less than x. So literally is the line y equals to x and then the upper region and the lower region. Okay, to show that the two set is open, how do you show? You need to show that for every point it is an interior point, right? So you need to show that every point you have an open ball, okay, that live inside the set. Alright, but can you do that or not? Can you do that? For any point in that set, can you avoid y equals to x line? Let me draw it. Okay. So you have this line here, and then you have y equals to x line here. Right. Okay. So my claim is the green part, the green part and the purple part are open. Okay. So if you are given any point, let's say in the green part here, can you find a ball or not that avoid the line y equals to x? You can, right? So you simply get the orthogonal projection here. So the problem is you need to prove why this ball will stay inside this region, maybe not intersecting the ball y equals, I mean the line y equals to x. Why? Because this is the orthogonal projection theory, right? This is the shortest distance to this line. Okay, if other direction should be longer already. So you need to use the theory from linear algebra. Okay. So that's so that's why I asked you, your minimum is achievable or not? Did you show it? Yeah. Achievable. Otherwise, you define a zero thing. Who knows? The minimum is zero. Who knows? I don't know. Correct or not? You need to check. You need to rule out the possibility. Who knows? Who knows? You need to argue. That's why you need to argue. That's why you need to argue, because minimum of a set could be zero. So you need to argue. You need to rule out the possibility. Okay. So I mean, even if you don't show in your exercise, but I still hope you need to learn this argument. Okay. Even though if I don't give you the mark to check this argument, you can just say, oh, these two regions are open. Okay. Even if I don't ask you to check, I hope you still learn to how to construct the argument. Okay, just that I don't require to write it down, okay, inside your assignment. But at least you need to know how to write it. Does it make sense? Okay or not? Everyone understand what I say? Understand what I say? Okay, so long thing short is you can use that these two regions is open, but you need to learn why they're open. Okay, although you don't need to write explicitly. Make sense? Yeah. So this question here, I want you to avoid using intermediate value theorem or mean value theorem. Okay, because this is the exact question I gave to my MA1 student. You guys have the same question. So in that case, they have to use intermediate value theorem or mean value theorem to solve it. Yeah. Hey, where is Si Yu, by the way? Si. No. Today got exam or tomorrow got exam or no? No.
Tomorrow.
Or tomorrow got what exam?
Compactification.
Okay. Yeah, question? Oh, okay. About this, okay. This is a good point. So in Cartesian, okay, in R2, right? What's the basis for this open bowl closed tube? You can use circle. You can use rectangle. Also can. I think we have shown equivalence between these. Yeah, inside the topology section. So I mean, last time, not last time. Yesterday, Gary pointed out a very important point, right? How we build topology. How many ways can we build topology? Okay, there are few ways, you know. Actually, there are few ways to build topology. At least 3 ways. At least. Okay. What are the 3 ways? At least we learn. First way is, sorry. Yes, we just assign. We call whatever set I want it to open, I declare it to be open. This is one way. Okay, I define it to be. Second way, yes, I tell you what set are open, and then I generate using basis or subbasis way. Okay? So I tell you who are the open set and then generate using these open set. Third way is the most basic way. Using what? Not quite. Metric, using metric. Okay, we use metric, the open ball. Okay, so I mean in the Euclidean topology, right? Euclidean topology, you can show that the metric, the topology induced by metric, okay, is the same as the Euclidean topology generated by open ball, for example. It's equivalent. So you can think of it as I declare open ball to be open, or you can declare that, oh, it is open using the metric set. Okay, that means what? The ball that has distance strictly less than r. Then okay, so typically when we move to topology, then we don't see this D anymore. We don't see D already. And we maybe don't see R also. Because no measurement already. Oh, makes sense? Okay. Hey, by the way, today I got a guest here. It's my brother, actually. Yeah, my brother. My brother is KieSeng. Okay, he wants to see me, what am I doing in my job. Last time, I don't know, I haven't tell you a story, right? Maybe I haven't told you. I told my MA1 student. Because I gave my MA1 test, I asked them to prove 2 times 3 equals to 6. How to prove? I'm not sure you guys know about piano axiom, about 10 steps like that. Right? Because we need to break 3 into 1 plus 1 plus 1 and 2 into 1 plus 1, and then you can use piano stuff. And then I showed this to my father. What do you think my father said? Hey, very good. No, before Tuo Ying, he said, 2 plus 3 equals 6. 3 plus 3 lah. 3 plus 3 6 lah. No, 2 times 2 times 3 2 times 3 And then I said no more. Then I showed him the solution. Then he said, so you're unnecessary. So I won't angry with you already because my father also like that. So I won't angry with the student anymore. So if you think pure max is unnecessary. But then what I told my father is, you spend money to ask me to learn this unnecessary stuff, and then now I use this unnecessary stuff to earn money. This is how I get my 6,000 per month doing this unnecessary stuff. Yeah, correct. Yeah. So I mean it's a privilege, I would say. It's a privilege to do pure max, You need to go to a certain height, only you can worry about pure max. For example, if you are Malay, like in a village, kampong, no money, nothing to eat, maybe even not enough clothes to wear. Can you think about epsilon delta? Crazy, man. You can't. Okay. So that's why when I first came back, before I came back, I was saying that Malaysia maybe is not ready for pure max yet. Okay, because people still worry about their living. They don't have time to go do this. How to say? Atas. Very how to say? Privilege. Yes. Only developed country can do this. Okay. So I already prepared. So I mean, maybe it proves to me that it's right because exactly not many students in the maths department want to do it. Indeed. Okay. So I'm still hoping to find counter example. So can you be one of the counter example? Can you be one of the counter example? In this case, I like counter example. I don't want my assumption to be true. If my assumption is true, then too bad. Time is not yet here. I hope to find counter example. Can you be one of the counter example? Yeah. Actually, I'm very thankful Yong Yan. I heard about Yong Yan story coming to study pure maths. Previously, you're studying finance, right? Yeah. The diploma. Business IT. Okay, and then he chose to come and do pure maths because you what? You what? Say it. Never mind. Say it only. Say it only. Yeah. 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 喜欢. So this passion, I cannot train you one. This is yours. Okay, I cannot train your passion. But what I can train is your ability, the max ability. This is the only thing I can train. Okay, so if you are patient enough, definitely I can train you. Okay, to my level at least. I'm not surprising you. I won't surprise my student one. You can be at least as good as me. So that's why you think that it's hard. All my assignment is hard, very hard, very hard, very hard. Because I want you to get to this level. Let me tell you a very real truth. If you get through this course properly, excelling, you will surpass most of the professors here. Any name you can name it. Seriously. But I'm not asking you to become very, arrogant. It's not like that. Okay? Just that this ability is not everyone that can handle. Okay, for example, my student here, this one, Sayed. You know, I teach him from the computer school, abstract algebra, and then I do this course. I see how he grows, you know. In the first year, he barely write English, you know. No English sentence on in his assignment. Just equation simply put together. Then I score him up. I give him feedback. Need to put some connective or what explain this part or what like that. Then in AA2, he did pretty well. He explained things well. I didn't ask him to write long paragraph. Also, I didn't do that. But it's enough to explain your thought, your solution. Then now he writes better now. And then I think if you have patience with maths, you will grow pretty fast actually. Maybe the starting point is hard. 万事起头难. Starting point is really hard. But afterward, you will excel pretty fast. Okay? Does it make sense? Okay. Okay, good. Let's continue. So we want to introduce this this two notion here. Apart from open cover compactness, we want to introduce limit point and sequential compactness. Okay, I mean to talk about these two, right? We need to recall what are the limit points are. How do you define a limit point? Okay, a point to be a limit point. So we say that a point is a limit point if every open neighborhood of x intercept A in some point other than x. Okay, can you imagine the picture here? So you have an x, okay, and then you look at every neighborhood of x. Okay. If you say that this x is a limit point of another set, then every neighborhood should contain some point from the set A. I don't know. Does it make sense? So this is a very good example, right? I mean, for the student in SMUM. Okay, actually, I quite painful the SMUM student. Like, you see that. Sorry, thank you. I mean, painful. What do I mean by painful? When I first came here, I saw that a lot of students like with couple, right? Boys and girls, couples together. A lot of couples here. So if you think, if you how to say, if your heart has a position for your partner, that means what? In every part in your life should contain this partner. every neighborhood of X should contain 2 instead. Otherwise, how can it happen? It cannot happen, right? If your partner is not your limit point. Right? Does it make sense? Okay. Yeah. And how to say sequence converges? Okay, because we want to talk about sequential compact. So sequential compact really just says that every sequence has a convergent subsequence. So how to say the sequence converge? Okay. So it converges, okay, to a point X if also you look at every neighborhood of X. And what happens to this every neighborhood? There exists an n such that Xn is in U for all n greater or equal to n. Meaning the tail, everything behind the larger n needs to live inside this neighborhood. So you can see these two definitions, the difference between these two definitions. For the sequential compact, you need to have the tail living in the neighborhood. But for the limit point, maybe 1 point in there, 2 point in there, infinity point in there, also never mind. It's kind of more general. As long as at least one exists, okay, that's not X. Right, so this is the difference between sequential convergence and this limit point. Okay, so then we want to see how this definition will differ. Okay, if we define compactness. Yes, question? Basically, limit point is what do you mean by limit? Because
sequence and point that it point the limit. The limit is not might not be the limit.
you say okay. But this wait, so take the example clearly again. If you take a okay, take a singleton one and then it is not a limit point, yes, and then it is okay, yeah, sure. So your limit is like which limit is that? What kind of limit is that? Or limit of the sequence. Okay, don't use limit. Here we use convert. So maybe just say that the constant sequence converges to 1. Is it? Yeah, converge to 1. But it is not the limit point. Right? Yeah. Yeah. So we want to try avoid using new word. If we're using new word, we need to define it. So unless I say, if the sequence converges to this point X, then we will call this as a limit. If you want, and then also can. Yeah. But so in that case, limit might not be a limit point. Yeah. Yes. So I think this is also one of the confusion point right last time when we introduced these two things. So make sure you remember this kind of example. Quite important to differentiate these two ideas. Yeah. Okay. So in this case, we want to define different compactness now. So let's define a set Y. Okay. So later we will reduce the result to we'll talk about result in metric space, but now we're still living in topological space. So a subspace of a topological space is limit point compact. Okay, it's limit point compact if what? If every infinite subset of Y has a limit point. Okay, I want this limit point to live inside Y as well. Okay, I want it to live inside Y. Okay, every infinite subset Y has a limit point living in Y. 2. A subset is sequentially compact. Okay, so sequentially compact if every sequence in Y has a subsequence converging to a point of Y. So note that when we introduce this definition, every word using in the definition we have defined. For example, what is infinite? We define already. What is subset? Defined already. What is limit point? Just record it. Okay, how about sequentially compact? What is sequence? Sequence is just S0, S1, S2, so on. It has a subsequence. What is a subsequence? So you just pick up some terms from your original sequence, okay, increasingly. And then convergent, we also define. So the two same thing here is the limit point live in Y and also the converging to a point in Y. Okay, have to happen inside Y. This is very important because if you look at rational number, it converge to something outside Y, outside rational number. Yes, so I have to happen inside. Okay, your subset. Okay, so far any question? Is this tool being introduced in ML2 or not? Is this tool definition being introduced in ML2? Sequential got limit point? Don't have limit point. Limit point compact don't have. Okay, sequential compact have. This is similar to what I study. I also study sequential compact and compactness. So this time we have this extra limit point. Okay, which I think is quite nice. Quite nice. It's quite nice. Okay. Okay, good. So the slogan here is, okay, what is the slogan here? The final goal we want to reach is in a metric space, limit point compactness and sequential compactness and the open cover compactness are the same. Okay, are equivalent. Are the same. Okay, this is the final thing we want to reach for this part. Okay, so let's prove some theorems so that we can know how they relate to each other. Okay, see how they relate to each other. So let's prove some theorem here. So theorem A, if A, so theorem A is compact, will implies limit point compactness. And B will prove that sequential compact implies limit point compactness. Okay, so this two result is hold true for topological space, any topological space. Okay, any topological space. For any topological space, this two statement is true. All right. So what time is it? Half an hour. Okay. So let's do which one? Let's do which one first. Okay, let's do A. Prove A quickly. So how should we prove this statement here? Compactness implies limit point compact. So if you want to prove limit point compact, what do you need to do? For every infinite set Y, it has a limit point in Y. Okay. But in this case, we will use contrapositive. Okay, so that if it is not limit point compact, then it is not compact. Okay. So how do we show it? So suppose there exists an infinite subset A of X. So we take the negation such that what? Which has no limit point in A. Okay. Take the negation. Okay. There is this one such infinite subset, there's no limit point there. Then what can you do? Huh? You want to show that it's not compact. What not compact means what? There exists a infinite cover that don't have a finite subcover. So can you cook up one infinite cover? Okay. Can you cook up one infinite cover? Then for every point in X, what can I do? I can take open set of X around X such that UX intersect A may be empty or it just contains X. Okay. If you cannot do that, then you will show that actually X is the limit point. Okay. So now C equals to UX over X in X is an open cover. X. So in this case here, you see the special part about this UX is UX intersect A can contain at most 1X. Okay. So what? If you take out any one of them, you might not cover one of the X. Okay. So since each UX cover at most one element of A, any finite subcollection of C cannot cover our infinite set. Okay, our infinite set. Because our set A is by definition an infinite set. Okay. So where's the technical part here? Actually, the technical part here is this part. Okay. The technical part is this part. Okay. If you don't believe there's an existence of a UX that looks like this, you should argue using contradiction. Okay. If you argue using contradiction, then you will contradict the not limit point compactness. Yeah. You need to argue by contradiction if you don't believe this existence proof. Okay. Suppose you cannot do this, then you need to contradict the assumption that you started with, which is not limit point compact. Okay. Next part. What's the next part? So next part, we want to show that if it is sequentially compact, then it is limit point compact. Okay, so here we will do direct proof. Okay, so suppose X is sequentially compact. Okay, and just let A be a random infinite subset of X. And then we want to show that it has a limit point in A. Let's say we call it A. How do we use sequentially compact here? Since we have already infinitely many points like that. So what sequentially compact says? Every sequence has a convergent subsequence. But now you got infinite set. Can you cook out a sequence? Sorry? Say again? There's one subset only, right? Only one subset A. So how do you cook out a sequence? Simply cook out. Okay, so now A must contain a countably infinite sequence. Because infinite just says it is not finite, right? So infinite could include what kind of cases? It could be countable, it could be uncountable maybe. But at least it must be countable. So I just take infinite sequence AN, okay, of distinct terms. Must be distinct, right? If not, then your set wouldn't be infinite. Okay, so you can pick distinct terms. Okay, countably many distinct terms. Okay. All right, so from sequentially compact, what can you talk about this sequence here? AN has what? And what is sequentially compact? Says every sequence has a convergent subsequence. So this AN also has a convergent subsequence. Okay. Subsequence. Let's say converge to some point in A. What do we call it? Little a maybe. Okay. So our claim is this A is the limit point. We want to show that this A is the limit point. Okay, how to show it? So how to show that some point is a limit point? Every neighborhood around this point, it must intersect A non-trivially. Okay, so every open neighborhood of A should intersect A. Correct? Because there's a subsequence and convergence. Okay, so A is a limit point of A. The intersection is the subsequence terms, right? Yeah, unique. So intersect A. Okay, yeah, good point. So other than because how we pick this AN, how we pick this AN? These AN are distinct terms. Okay, we don't get into the constant business here. Okay, there's no constant sequence coming in here. All these AN have to be distinct. Okay, so the counter example we gave for the constant sequences now doesn't become a problem here because we are dealing with distinct terms. Okay, distinct. Okay. Any question? Got question or not about this proof? Yeah, this is quite important other than A. Okay, if no question, let's continue more. So feel free to stop me anytime if you want to come back. I will arrange my own time. So limit point compactness. So you see, what we have done is we only go two directions, compact to limit point, and then sequentially compact to limit point compact. So there's one example says that a limit point compact doesn't imply compactness. So the converse of A might not be true. Okay, let's look at one example. So limit point compactness might not imply compactness. Okay, so look at this example. I think it's quite nice. So let's say we give Z the topology. Okay, having a basis such that it is encapsulating 2n and 2n plus 1. So it's the consecutive even and odd. So maybe let's draw some line here. So we have 0, 1, 2, and then let's say -1, -2. So how does this open set looks like? So it's like 0 to 1, and then -2 to -1, like that. 2 to 3, like that. Make sense? Okay. Intersection, you need to see it as an intersection. It's not a real interval here. But I draw it on the real line. Okay, view Z as a subset. Okay, subspace. All right. So clearly what? This basis here is an open cover of Z. Okay. Does it has a finite subcover or not? If you take out any one of them, right, you shouldn't cover the two number already. I don't know. Okay. Because if you take this as your basis, what does it mean? You can consider their union. I don't know. If you take out one of them, then no one will cover 0 and 1, for example, in this case. Okay. So this basis is an open basis with no finite subcover. Okay. So this base is not, yes. What do you mean? What do you mean? What do you mean? Oh, sorry, sorry. I mean, this one should be just 2 point, right? Just 2 point. Yeah, just 2. Because I mean, our Z is a discrete set. And then I want to draw this line because I want to have an order on them. I want to arrange them in order. So you can ignore the line actually. Yeah, ignore the line. Yeah, but this one is a typo here. Yeah, this should be just a 2 point set. I just want to declare the 2 point set to be open. That's all. Okay. Is it clear that this basis covers that and doesn't have a finite subcover? Is it clear? Okay. If you take any one of them out, then you won't cover the two number already. Okay. Okay. Good. So, however, we want to show that it is limit point compact. Okay, we want to show that it is limit point compact. So, how to show? Every infinite subset of A, okay, in this set, it should have a limit point inside A as well. So, how to show this? How to show this? Limit point compact. There's only one neighborhood. Yeah, sure. Mm-hmm. But is this like, okay, so let's say, okay, if you have an infinite subset of A, right, of Z, if 2n is in there, then 2n plus 1 should be the limit point of A. Okay, but 2n plus 1, should it be living inside A or not? No. Yes. Yes or no? No. No or yes? Mm-hmm. Yeah. It's excluded. And then it is not in there. But it has to be true for all infinite set. Okay, right? Yeah, so what's the problem here? But the claim is this is limit point compact. Okay, let's think about this, whether this is, so the claim here is, There's this part I missed here. So the claim here is Z is limit. Let's see if this claim is correct. Okay, wait, let me check the definition of limit point compact. It's a limit point in Y, correct? A limit point in Y. Oh, okay. Okay, let me see. Every subset of Y. Oh, okay. So let's come back here. Come back here. Okay. So what does this mean? That every infinite subset of Y has a limit point in Y. Okay, so this subset here is A, for example. Right? Okay, A has a limit point in Y. Okay, just now what do we want to show? We want to show that Z is compact. So if we can show that every infinite subset of Z has a limit point in Z, then we are good. Okay, it's not coming back to the subset. Oh? Okay, the limit point is not living inside the subset, but in Y is enough. Does it make sense? Okay, now. But the point on sequential compact is what? Every sequence in Y, okay, converge to some points in Y. Okay, but for infinite subset, it's a subset of Y. The limit point can live in Y, not living in A. So in this case here, what happens? Okay, so given an infinite. So let's finish out this and then we will adjourn the class. So given an infinite subset A of Z, okay, if 2n is in A, then who is the limit point? 2n plus 1 is a limit point because that is the only open neighborhood that contains 2n. Okay, 2n and 2n plus 1. Okay, so 2n plus 1 is the limit point of A. But if 2n plus 1 is in A, then who is the neighborhood that contains 2n plus 1? Only the neighborhood that contains 2n and 2n plus 1. Okay, so every neighborhood need to contain it, right? So 2n is a limit point of A. Okay, and then 2n and 2n plus 1 are clearly in Z. Okay, so it is limit point compact but not compact. Question before we break? Any question before we take a break? Okay, so far so good. Okay, so I will try my best to come up with my lecture notes earlier because I have to deal with MA1. Yeah, MA1 very tedious. A lot of detail. I need to write all the epsilon stuff come out for them. Okay, yeah. So please be considerate. I will do it soon. If not, you watch video first. Okay, yeah, watch video first. If there's something wrong or what, you just message me, tell me, let me know, and then see if it is my mistake or just some misunderstanding. Okay, yeah, feel free to contact me. Okay, see you next Wednesday.
就会去有讲，它是 limit point compact。
Yes,
它是 not
not compact. Yes.
你可以再解释一下